In the previous chapter, we already discussed, already give a lecture on what is the chemical devices, okay, functional products as well as formulated products, and what is the differences between the chemical devices with the functional product. So I hope that you can differentiate between these two types of the products, chemical devices and functional product. The main difference is on the they have inlet or out, and also outlet for the chemical devices, while functional product doesn't have any outlet or inlet. Okay, so that one is the major differences. Okay, and formulated is a composition of the mixture. Okay, so you mix all the components so that you can get the formulated. Okay, the examples for the chemical devices is like what is it? Like a faucet mount water filter. Okay, water filter with the activated carbon inside, so that we can remove the organics or metals. Okay, reverse osmosis water filter, and many more. And functional products, for example, is like what is it? Your mask. Okay, what else? The barrier. What is the barrier? The food packaging, right? Okay, that's another example for the functional products. While for the formulated products is you use in daily life, like cosmetics, okay, detergents, right? Inkjet printer, that is a formulated product. Okay. So in order to design this all this type of the products, so you need the mathematical modelings. Okay. For example, like a Langmuir kinetics, right? Kinetics is Langmuir, desorption, absorption of the maybe if you want to design the what is it, air filter, right? Okay. So you need the Langmuir equations. Okay. What else? Like fixed law, okay, the viscosity. So that is the mathematical modeling that you have to use to design your products. Okay. So for today's, okay, for today's we will continue on how to design the chemical devices. Okay. I think today we will focus on the how to design the chemical devices within this 1 hour. Okay, and then I give you an assignment. So you have do with your group members, okay, and submit through the e-learnings lah. I don't think we can do in our class, okay, because generally is involving the mathematical modelings, okay, and uh, for the design of the functional product, maybe for the next class, in for 2 hours class, okay, together with the functional product, together with the formulated products, how can we design these products? Okay, I think we need a long we need a long period to to explain this functional product and also chemical products, formulated product. Okay, I think for chemical device is quite short. Okay, so I can explain in within one hours lah. Okay, to design the chemical devices, actually we need to consider. I think we need 4 steps to 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 design this chemical device. First, step 1 is you need to specify the product performance. Okay, and then you need to identify the key ingredients. After that, the configuration is the shape, form, right? That is configuration. And then the last step, I think, so you have to use the model, okay, to identify the product specification. That is the 4 step that you have to use to design the chemical devices. Okay. For the chemical devices or functional product, the main thing or the main criteria that you have to consider is the key ingredients, type and the amount of the key ingredients. That is the important. Okay, for example, if you use catalyst, that is the key ingredients. Okay, for the air purifier. Okay, and then the structure with these ingredients. Okay, we have to configure it and also identify. Okay, so The key ingredients, we refer to component that is a very important or essentials, okay, in order to achieve, in order you want to achieve your goals, okay, or you want to achieve the desired outcomes, okay. For examples, for the air purifier, okay, for the air purifier, you need catalyst, titanium oxide, because you want to decompose the volatile organic compounds, okay, using photocatalytics, okay. So the key ingredients of the catalyst is important, okay. So we call it as also as key chemical ingredients lah, okay. And another criteria also we have to consider lah, like the size, all right, the size of the filter, the position of your what else, the position of UV, the position of the catalyst, that one also you have to consider lah, okay. For the water filter, okay, water filter, the key ingredient is like is a activated carbon lah, or ion exchange resins, because you want to filter, right, okay. So that is important, okay. Similarly also, if you use a reverse osmosis, what is the important, that one, okay, the membrane, right, that is the important, okay. And then the amount and the configuration of the key ingredients are fixed, so that we can meet the required product performance lah. Okay, for devices, okay, product performance generally we quantify by using the component concentration, okay, and the flow rate of the feed and also the outlet, because chemical device they have a inlet and also outlet, while the functional products we have to measure by the degree of to which the product achieve its design functions lah. Okay, or if you want to design the what is it, uh, a mask, right? Okay, so is function or not? Okay, so that is the functional product lah. Okay, so if you look at here that design procedure for the chemical device and the functional products, actually we have to specify the product performance, okay, and we have to also identify the key ingredients. This is the main things, okay, the key ingredient, okay, and then identify the physical chemical phenomena, okay. So this is the step lah, meaning that first step is the specify product performance. Second is you have to identify the key ingredients, okay. The third one is you have to identify uh, the physical chemical phenomena. Say number two, including the configuration, okay. Configurations meaning that the size lah, okay, the mechanism also, okay. So how you want to decompose, for example, to decompose VOC, right? What is the mechanism, okay. And step 4 is the models. You have to use models, which is mathematical modeling, okay. Experiment to confirm, and use the available and knowledge to compare, okay, to compare with the product alternative, okay. This is the 4th step you have to use for the chemical device and also functional products, okay. Okay, is it clear? This step you have to remember, okay. Product performance, key ingredient and configuration. Key ingredient is the compound, okay. Configuration is like a shape, okay, the size, that is configuration, okay. And then physical chemical phenomena, and as well as models and experiments. The models, this one is you have to use the calculation, the mathematics, okay. What you have learned in the thermodynamics class, okay, chemical engineering thermodynamics, mass and energy balance, okay. You have to use that knowledge, okay. Chemical reaction also, okay, you have to use that knowledge, okay. So I think if you not remember, I think you have to find your textbooks, how to find that all the equation, okay. Okay, for examples, we want to design the air purifier, okay, because volatile organic compounds are emitted as a gas or volatiles, okay, from certain solid or liquid, especially from household products. What is the VOC? If you look at here, that even for paints, okay, they have this kind of the VOC. Benzene, this is very is carcinogenic, benzene. toluene, xylene, ethylene glycol, formaldehyde, methylene chloride, okay, tetrachloroethylene, and 1,3-butadienes. Okay, so if you can have paint and varnish, right, and wax, okay, contain all organic solvent. Okay, even especially paint for the very old house, right? That one can the content of the VOC is very high. Okay, all very old house. Okay, so all these product can release the organic compound. Okay, uh, what is the effect to your body and also for human and also environments? If you look at here that um, had effect to eye, nose, and also throat irritation, headache, okay, damage to liver and also kidney, okay, some organic can cause cancer. That's why if you can use to, if you can find a component that can replace these components, okay, these carcinogenic components, okay, so you should use that alternative components, okay, which is more less hazardous, okay, and not and more environmental friendly. Okay, okay, so how can we design this air purifier? Okay, uh if you look at here, okay, the scenario is I think at your home also you have this air purifier. Okay, many company produce this air purifier, okay, like a Koei, Kuko, and many more lah. LG, right? What else? Samsung, I'm not sure Samsung. Okay. A home appliance company plans to produce an air purifier to remove indoor volatile organic compounds. This is VOC lah. As a measure, okay, as a measure of product performance, it is expected to reduce the concentration of VOC from 150. So meaning that this one is CO naught. Okay, CO naught. Concentration, okay. If you still remember chemical reaction, okay, chemical reaction class, 230 milligram per cubic meter. Okay, this one is CF final, right? And a room of 2 meter cubic. This one is volume of room. Okay, this one. In size within 2 hours. So whether we want to store these volatiles, or we want to decompose, or we want to just absorb and then we release, is depending on your design. Okay, generally VOC, we doesn't want to just store, right? We want to decompose and release. Maybe if you want to, after we decompose, we convert it into another components like a, what is it, like a CO, CO2, okay, H2, okay. So the decomposition is the main thing, okay. Okay, the first step is, what is it? First step is, if you still remember, okay, how to design. The first step, this one. Okay, please specify the product performance. Okay, product performance. What is the product performance? VOC made up from the different compounds like acetone, benzene, toluene, and also methylene chloride. Right? But we, as a starting point, okay, we just choose one, maybe toluene, benzene, because even if you want to start your research lab, you have to use the model compound. Okay, not we starting with the mixture. Okay, because this one, after you design these devices, okay, so you can consider, you can upgrade it, okay, um, by using other compound, okay, such as the toluene and such as acetone, benzene. But for now we choose a one model compound as a toluene. Okay, so we can absorb only toluene lah for this design. Okay, after that you upgrade lah. Okay, because first, after you finish design this one, you have to produce the prototype. Okay, you have to test. Okay, and then you try with the other components lah. Okay, which is can represent for all other volatile organic compound, VOC. Okay, okay, okay. So for the starting point, okay, toluene is used as the reference compound. Okay, reference component is a starting lah. Okay, or model compound for quantifying the product performance. Okay, so please remember this your conditions. Okay, initial concentration, final concentration you want to decompose, and time is 2 hours. Within 2 hours, meaning that not more than 2 hours. Okay, you can reduce within the target. Okay, the volatile organic compound. Okay, so how can we remove this VOC? Okay, they have 3 methods. Okay, so if you look at here, okay, the 3 methods, right? Adsorption is a capture, absorption both is capture. Only the difference is for adsorption is uh, if absorption is just on the surface, right? Absorption. Okay, so if you have particles or VOC, it's just absorbed on the surface. Okay, if this one is the inside the catalyst lah. Okay, so it's just absorbed on the surface. Okay, this one is a surface, this one is interface lah. Okay, surface, this one interface. Okay, but absorptions it should be go inside the interface. Okay, should go inside the interface. Particles soak into the bulk of the other faces lah. This is we call it as an interface lah. Okay, and then we capture, we just store without decompose this VOC, right? Okay, which method is do you think you have to consider for your devices? All right. Okay, and the last part, the last choice is photocatalytic oxidation. This one, after absorb, okay, we will decompose lah. Not really absorb, but they have a reaction and separation, right? So once they absorb, do some reaction, and then dissolve as another product, or maybe another volatile. Okay, this is the difference. But for VOC, of course, we want to decompose. That's why we choose this one. Okay. So the reason because PCO, okay, photocatalytic oxidation can decompose instead of just capturing VOC. Okay, so we select this method. Okay. So among the various of the PCO catalyst, okay, because catalyst is the main ingredient. Okay. Boleh dengar hujan je. Saya rasa macam bisa juga. Saya tutup tingkap je. I close the windows. Okay, now it's raining outside since morning. Now it's still morning, but early mornings it's so heavy. Okay, what is the mechanism? If you look at here, decomposition done by the catalyst with the presence of the UV light. UV light. Titanium oxide is the most widely used of the PCO. So meaning that titanium oxide is the key ingredient. You have to remember that one. Okay. Why titanium oxide we use? Okay, because first if UV, of course, UV light generally we use a titanium oxide because one is a cheap, reasonably priced, and then the supply, right? Even if we do in my laboratory, we one of the researcher using UV light to decompose or do the reactions. Okay, they use the titanium oxide lah, because the supply also is quite plenty. Okay, and then in terms of the reactions with the UV, okay, so the activity is more efficient, and then the capability to absorb the reactant or the VOC is much better than other catalysts. Okay, and then generally this catalyst, okay, this component, this one, we put on the support. Okay, if you still remember, if you learn in the chemical reactions organic side, we have the support, right? We have the support, and then we put we mix with the other metals. This one metals. Okay, as generally we need the support. Okay, we need support like a carbon, alumina, silica, nickels, okay, ceriums, and so on, or char. We can use as the support. Okay, to increase the surface area or the intact between the titanium oxide and also VOC or UV lights. Okay, all those things we have to consider. Okay. Okay. So this is the difference. If you look at here, absorption and desorptions. Okay, this one already explained, right? absorption and desorptions. This is molecule drawn to the bulk of the phase. This one is only adhere on the surface or stick on the surface of the catalyst. Okay. And then what is the mechanism? As I told you, once this is a UV lamp, right? Is UV give a heat here to the photo. Okay. So it will actually how to say produce the radical actually. Okay, radical. Okay, because water also gonna absorb here. Okay, H2O. Okay, so this will cleave H2O bonds. Okay, so once we cleave the H2O bond, this one. Okay, so we produce OH radical, hydroxy radicals. Okay, that is the reactions. Okay. Okay, and then these radicals will react with the VOC lah, and after react with the pollutants, this one, right? Okay, so we will release as maybe a water volatiles. Okay, because VOC organics. Okay, CHO. That's why you can produce water what is it? Volatiles in term of the vapor, water vapor lah. Okay, and CO2. Okay, so we converted to other components lah. Okay, this is which is not harmless. Okay, when we decompose these pollutants or VOC, okay, we converted into harmless components lah. Yeah. Okay, so this is the mechanism. Okay, so another one thing is how can we place this catalyst? Okay, so how can we place catalyst? Whether if you have a system like this one, right? Maybe you want to put in the middle or on the side, this one, right? This one. So it's up to you. But we have to do experiments and modeling. Okay. So and then we have to support put also uh, the the catalyst support. Okay, that is very generous. Okay. So how can we design the air purifier? Okay, how this is more to the configurations. Okay, configuration, how to design after key ingredients. We look at the configuration, the structure, the form of the air purifier, whether you want to make what shape, triangle shape, the air purifier, or cylinder, right? Or what is it? This one, okay, rectangles, okay. The main thing you have to consider that provide intimate contact between the catalyst and also airflow. Okay, because the airflow have VOC, so should be contact with the catalyst, right? Okay. Of course, we need the pump or something that can absorb that airflow, or airflow can easily go inside your air purifier. Okay. Allow sufficient and relatively uniform UV light. This is to hit that to do the reactions. Okay, to hit the catalyst and also your VOC. Okay, and then be compact because maybe it should be portable. Okay, not really big. Okay, because we have only little space. Like we design the what is it? Apa kita panggil water purifier, right? Okay, generally is very portable lah. Okay. So it is decided that commercially available is a PT dope titanium oxide. So we use a platinum as this one lah. This one is as a support. Okay. So we can impregnated. We have to put lah on the HEPA filter. So we have a what is it? What we call not the storage but alamak hang pula. Dari semalam mesti ada hang. Okay, maybe you put in the you store inside, you put inside the casing. Okay, the catalyst and also the catalyst lah, titanium oxide with the platinum. Okay. Okay, so and then you identify the configurations. Sorry, I have to update this one. Okay, because I think the previous figure, this one is a cylinder shape, right? Okay, so I just update according to the in the book text, okay, to see the difference. Okay. So if you look at here that for this one, okay, they have HEPA filter here, UV lamps, right? And then is a fan here, okay, fan or like a pump. This is the inlet, okay, and this is the outlet, okay. So this one is a very curve. The curve of UV lamps, UV lamp you place within the this one. What is it? The filter coated. This is the catalyst you put here, right? Okay. So airflow, and then airflow here, and then close contact with the catalyst. Okay. This one, and then go outside. Meaning that the reaction occur here. Decomposition occur here, right? Okay, and then go H2O and also CO2, okay, HX lah, and so on. Okay, that's another one. And figure this one. If you look at here, UV lamp you put at the center. This one a little bit this side, right? Okay. So inlet. HEPA filter is more compact lah here. Okay. So to have what is it, the contact side, and then outlet go outlet here. Because HEPA filter is here, right? On this side. Okay, this is another. And then see the design is different. Okay. Although at the center, but this is, I think, we want to increase the volume actually. Okay, I don't think this one is a good design actually. This is seems like a much better lah. Okay, we do the assumption after that. Okay. Okay. So after that, we identify the physical chemical phenomena. This is the mechanism lah, or the reactions. Okay. So if you look at here that the composition of VOC actually due to the redox reaction and also producing the hydroxy radicals. Okay, so if you look at here that electron pair holes, right, H2O on the surface. This is more to Langmuir actually. This is a we call it as a bimolecular reactions. Okay, if bimolecular is a Langmuir. Okay, together, and then this one is produce CO2, H2O, and HX. Okay, and this is a redox reaction to produce H2O and CO2. Okay, so there has an absorption and also desorption. Okay, we decompose that VOC lah. Okay, so the main things is Langmuir, Hazelwood, kinetics. This one, if you still remember, I think you already learned in the chemical reaction engineering group. Chemical reactions. Cost. Okay, so how to use this one? Okay, if you still remember that rate of reaction must be what is it, like the equations, okay, like R equal to negative K dCA over dt, right? You still remember. Okay, so this is the rate of reaction. Because why we consider this rate of reaction? The main things is decomposition within 2 hours. That's why you need this Langmuir Hazelwood. Okay, 2 hours, within 2 hours, and it's involving the concentration, initial concentration, and also final concentration. Okay. Okay, so by the Hazelwood equations, okay, if we consider air perfectly mixed, okay, and you consider the mass balance of the toluenes, right? Okay, so it actually is if you look at here, R toluene, right, go to negative K, after that negative K theta T and theta water lah, because there's a bimolecular, right? Air, there's a water also, and also toluene. If you still remember, negative K Ca C alpha lah, C alpha, C beta. Oh no, Ca C alpha and beta, right? Okay, but if we consider this one is actually is water is excess, right? Because at room, right, water vapor is excess. Okay, So this one we can consider theta omega is equal to 1. Okay. So it's just a fraction. Okay, just equal to 1. Okay. So from these equations, you can expand the equations. Okay. Right. Once you this one, right? R RT lah. Negative K theta T theta water. Right. This is just a fraction of the concentration lah. Okay. This is excess. Okay. Excess. It is very excess. So that's why it's close to 1. Okay. Okay. So we can rearrange this equation. This one will be actually is KT lah. Okay. Okay. And then you can get concentration equal to theta T lah. Just rearrange the equation based on the Langmuir. And then this one we just substitute into this equation. Okay. So you can get this one. Okay. The composition rate of the toluene. Okay. So finally, if you substitute this one, okay, substitute this one to this one, this equation, so we can get this one. Okay. Rate of reaction. But if you look at here, this one, right? Okay. So you need the integration, knowledge of integration. Okay, if you do integrations, okay, T final and also T naught. Okay, this one is T final to hour, right? Okay, this one is from 0. Okay, so you have to rearrange the equation until you get this one. Okay. Okay, so now we consider the decomposition rate. Okay, decomposition rate. Okay, KT is if you look at here, there's a KT, right? K. Okay. KT is a ratio of the adsorptions. Okay, and K is actually this is we can get data from the other references. Okay, K is for the fitting parameter or the regress parameter. Okay, so if you look at here that KT, we can get this one. This is from the reference. Okay, from the reference. Just substitute into the previous equations. Okay, so that we can get the TF. Okay, so we can get this one. Okay. Okay, if you substitute into the previous equations, okay, must be below than 2 hours, because after 2 hours, meaning that your product is not meet the specification. Okay, must be below than 2 hours. Okay, so 2 hours, TF must be below than 2 hours. VR, room volume of the room, so 2000 meter cubic. Okay, so we can get TF. Okay, TF is below. So what we have to calculate is V of the catalyst. Okay. So to get the V catalyst, we have to determine by using the composition of the toluene, composition rate. Okay. So this is a first rate of decomposition. Use the model, right? Okay. This is a step 4. What else do we have to consider? The configuration, the volume of the catalyst, and also the volume of your, maybe the volume of your air purifier. Okay. So if you look at here, if we consider the volume of the catalyst, okay, if you look at here that catalyst coating, right, the amount, okay, 14.4 lah micrometer. Okay, after we consider L 32 centimeter and D equal to 10 centimeter. Okay, so the area is 0.1 meter square meter. Okay, so this is by the assumption. Okay, after that, what's that? The important one is the light intensity. Okay, because you use the light to heat that VOC, so can have a reaction with the catalyst, right? Okay, so first is the decomposition rate. Second is the volume of the catalyst coating, how much? Okay, and then the last one is the light intensity, okay, by Beer's law. Okay, light intensity is based on the Beer's law. Okay. So based on the base law, I lah, this one. This is I'm not really familiar with the light intensity. Okay. So this is the equations. Okay. If you substitute all the equations, I naught, okay, epsilons, UV light absorption, and rho b. So you can get what is the light intensity. So for 14.4 of the catalyst coatings actually is similar lah with the I naught. Okay. So meaning that it's meet the specification. Okay. Okay. Actually, we have any design issue lah that you need to consider. Not only the just now I told you only toluene, right? Okay, but you have to consider also other components. Okay, I think you can upgrade. Okay, before you do the prototypes, you test also by using other VOC like what is it? Other VOC. Okay, maybe like benzene, right? Uh, ethyl benzene, right? Which is more polar. Okay, maybe non-polar or polar compound. Okay. What else? The design of the HEPA filter, because sometimes it's going to be clogging, right? Too much is going to be clogged. So we have to consider that. The size of the fan of the pump, right? Fan, this one. This one also you have to design. Okay, this one you need to consider. Just now we just consider the filter, the catalyst, UV lamp, right? Okay, and also the packing. Okay, fan maybe you also can design. Okay, by using what is it, mass and heat transfer, mass transfer. Okay, equations. Flux, right? I'm not sure for the mass transfer, mass transport. Okay, and then in terms of the relative humidity, okay, that one also you can design. Okay, so anything that related with the your goals or your objective, okay, so you can design. At least it can decompose the VOC within 2 hours lah. So we can reduce from 200 or 150 to 30. How much we want to reduce this one? 150 milligram per cubic meter to 30 milligram per cubic meter. Okay. Okay, any questions about the step? Okay, so actually this one is not your activity lah, because I already give the answer. Later I will put in the in the e-learnings. Okay, you have to do this. You have to design the faucet amount water filter. Okay, this one lah, if you still remember. Faucet. Where's the faucet? This one. The mount filter. Okay, this one. Okay, and then you have to discuss with your group. Okay, I'm still not finished this one actually. You have to do the kinetic. Okay, almost finished, right? You have to do the kinetics as well as product specification lah. Okay, so you have to do in your group and design and you have to discuss. Okay, any question about the step how to design the chemical devices? Actually, the same step also we can use for the functional product. Okay, but this one is we will discuss more later. Okay, in the next class together with the formulated product. Any questions? Okay, so please submit. I will upload today. Okay, this one we can call also as a tutorial assignment also. Okay, please do this one and submit before next class. Okay. Okay. So Doctor share back the QR code attendance. Okay. That's all for today. Thank you very much. Okay. I share the attendance. Okay, that's all. Thank you very much.